This is our demo video for our project AI ML for electric distribution grid outage analysis. Thanks to the support from Vernova, Armina Proton, and Dawson Zhang. All right, this is our problem statement. So power outages are a massive inconvenience and a lot of time are induced by destructive weather. This project aimed to target highly populated counties within a single state and combine outage and weather data from each county over a short period of time. AI models were used to test and train this data in the hope of being able to predict power outages based on weather patterns. Two main objectives we had for this project was the development of an AI or ML-based outage prediction model to predict power outages by historical data and weather conditions. And then secondly, to develop an interactive and intuitive visualization tools to present predictions made by the model.
Right, and to outline the requirements needed to obtain those objectives, we first needed to collect outage and weather data to be used in our models. We then needed to use Python to clean this data and develop, test, and train said models. We also needed to upload all this code onto GitHub to store everything and document it for future use. And we also wanted a website so that any user with the appropriate data can upload the data and have our selected model feed an output of a power outage prediction. Okay, and to implement this, we first selected Florida as a county the state we wanted, and we selected 4 counties from it: Orange, Miami-Dade, Broward, and Palm Beach. We collected weather data from the National Centers for Environmental Information and Open Weather. The outage data we gathered from poweroutage.us, and we collected all this data hourly over the 3-year period from 2021 to 2023. To clean this data, we first had to numerically encode qualitative data, such as weather conditions being labeled as rainy, overcast, or sunny. We had to label them as 0, 1, or 2, and so on for however many weather conditions we had. We also had to put in a new feature that indicated whether the data point was collected on a holiday or weekend, because those can also impact power outage predictions. And we also had to remove all the redundant features. And afterwards, after cleaning everything, we also had to cluster it by dbScan. And for training the models, we first started with basic machine learning models, such as linear regression. And then we moved onwards to more sophisticated models like transformer and time series models.
In our first several try in feeding our data to the model, our result was even worse than the pure guessing because of the outliers in our data. Our solution is to use the clustering method to identify the outliers and then remove them. The method we use is called dbScan, which is grouping together the closely packed points and then marking the points that lie along in low density regions as the outliers. There are 2 parameters to the dbScan algorithm. The first one, minimum point n, is the minimum number of points required to form a dense region. And the epsilon defines the radius of a neighborhood in terms of distance. Our parameters are all 5 for the minimum point n and the epsilon. The core feature of dbScan is its adaptability in discovering the clusters of varying shapes and sizes. And we have 16 features to the weather and outage data gathered in the real world, which means they have complex structures. So the dbScan performs well among our other approaches like the IQR method. And as you can see, the rightmost picture is part of our result. For the dbScan method, for each cell, the right one is before the dbScan, and the left one is after dbScan. And you can see many outliers are removed by the dbScan. And then let Lexman to introduce the primary model.
Yeah, Before moving to sophisticated ML or AI models, we experimented with basic models like linear regression, SVR, tree-based models, ENN, etc. Provided the results of these models are not satisfactory, we then decided to move to transformer time series modeling. The results of the tree-based modeling are shown here. The left image corresponds to the error given by each tree model, like random forest, GBDT, XGBoost, etc., with the baseline corresponding to the outage average values. The right image corresponds to the confusion matrix exhibited by outage percentage values with class 1, 2, 3 labels established by taking the outage values from minus infinity to 33 percentile quartile range as class 1, 33 to 66 range as class 2, and 66 to infinity as class 3. In the next slide, we plotted the true versus predicted values as regression line plots and also investigated on a surface level by compressing the feature size to 2 using t-SNE and examined the model's prediction on a surface level to make sure the models were following the nature of the given data. After the series of experiments only, we decided to move to transformer-based model, which will be explained by Ify.
We have tried the transformer model built using PyTorch. It includes one input projection layers, which can project the features to a higher dimensions, followed by two transformer encoder layers, which uses self-multi-head attention mechanism and forward neural networks. And then we use a global average pooling layers to make the average of the whole layers. Finally, we use one linear output layer for the regression prediction that we can get the predicted power outage value. Then in the next slide, in this slide, we show the performance of our transformer model. So we can see our predicted values can fit the actual values well, and we can achieve R-square score to reaches to 0.65. Next slide.
So we have created a web application using Streamlit to demonstrate our results. So Streamlit is a popular open source application framework, and it is specially designed for machine learning and data science related projects. So the app is deployed locally and then made accessible over the internet using a local tunnel. So the main advantage of using this local tunnel is its accessibility. The local tunnel makes the locally hosted application accessible from anywhere without needing complex deployment on cloud servers. So here we enter the password for the local tunnel, and this will make the website accessible to anyone on the internet. And the website would ask us to upload uh, the data set for whose prediction we want to analyze. So here we upload the data set. And the model which gave us the best results in terms of R2 score and mean square error was the time series model. So here we have created the website for the time series model to showcase our results.
Okay. In time series, we only use the time and outage as a feature and result. First, we plot the 7-day average moving line and observe the trend of data. With this, we can basically see that using the time series method is feasible, but the time window need to be reconstructed. So we use the sliding window to reconstructing the data set. By changing the window, the past data is used to predict the future data. For this data, we tried a different model to predict the and gradient boost achieve the best result. So this graph is show the relationship between the actual and predicted value, and this residual plot show the relationship between the actual value and residuals, and the closer the distribution was to the line, the more better the model was, and for this fitting image, the tensors through the sliding window predict better than the moving average line as the baseline.
All right. So just to wrap it up here, to include time series is the best model determined by the R squared and MSE values. 0.77 and 0.0065 respectively. And I guess just to look towards a future study that could be done, we would want to find where this outage occurs in transmission lines to provide an even more helpful result for the similar study. But thanks for your time, and we appreciate it.